In today's video, we're going to be talking about definite integrals and definite integration. We talked about indefinite integration in the first lesson on integrals in this series, but let's talk about definite because this tends to be a lot more useful than indefinite integration. When we talked about indefinite integrals, we always solved an integral that maybe looks something like this, say x squared dx. And the answer to this was x cubed divided by 3 plus c. But why are we always writing this plus c? I mentioned it in the first video. It's because we don't know if there was a constant here whenever we did the integration. Remember, if we take the derivative of a constant, it equals 0, so it's possible that if we take the antidifferential of x squared, there was a constant before, we just don't know what it is. But this is also just our answer when we solve this. What we're going to do is we're going to add an a value and a b value to our integral in order to make it a definite integral and find the area under a curve in a specific area, so that way we get a specific answer. But before we go around solving definite integrals, I have one definition for you. Let me write it down here. So for our definition, we need to let f be defined on a comma b, the closed interval a comma b. Remember, brackets means closed, so we include endpoint a and endpoint b. We say that f is integrable if the limit as delta x approaches 0, remember we talked about this last time in the definition of the integral. If you haven't watched that already, I'll leave a link to it up here in the top right corner. If the limit as delta x approaches 0 of the summation k equals 1 to n of f of xk times xk exists. This is our definition. One thing to remember, delta x in this case is equal to b minus a divided by n. This b and a here divided by n. And xk is equal to a plus k delta x. If you watched the last video, you may recognize this as the Riemann sum. And that's correct because that's exactly what this is. If this limit exists, then we have a definite integral on the interval a to b, and we can find the area under that curve. So let's do an example using this Riemann sum. I will tell you now that we will not be using the Riemann sum to solve all definite integrals. That's just what we're going to start with. In my next lesson, we'll talk about how to solve definite integrals without the Riemann sum. But for now, we're going to use the Riemann sum. But before we do that example, let's talk about a little bit of notation. I'm going to draw an integral symbol here. Remember, it looks like this very elongated S. I'm going to write an a down here, a b, and then f of x dx. This is what a definite integral looks like. A is our first value in this a comma b interval. So say that our a comma b is, 3, 7. Down here we would write 3, and up here we would write 7. This is the bounds of our integral. And f of x is whatever our function is, say x squared, 3x cubed, whatever we want to put in there. Dx represents the variable that we are integrating for. This could be dy, dz, do, whatever letter you want. For our purposes, we don't have to worry about other variables, so we're just going to use dx for 99% of equations. Okay, now let's do the example problem. This example asks us to estimate the integral from 0 to 1. By the way, when we're talking about definite integrals, we go from the bottom variable to the top variable. So estimate from 0 to 1 x squared dx using left endpoints and using equally spaced subdivisions. The equally spaced subdivisions means that the width of our rectangles and our Riemann sum will be the same. Let's do this example problem now. And we may as well use a different color. Let's use green for this example, why not? So the integral from 0 to 1 of x squared dx is equivalent to the limit as delta x approaches 0 of the summation of k equals 1 to n, but of what? Well, we do need to find a couple numbers here. First of all, we know what a and b are. Remember, our bounds of our integral are a and b. So our a comma b in these closed brackets is equal to 0 comma 1, which also means that our delta x is equal to a minus b over n, which is equal to 1 minus 0 over n, which is just equal to 1 over n. Our xk is equal to a plus k delta x. Well, we know what a is and we know what delta x is, so we may as well just plug it in. So plugging this in, we get 0 plus k times 1 over n. But we do have one thing that we need to address. We start at k equals 1 whenever we do these summations, but our integral starts at 0. So we have to turn this k into a k minus 1 instead of just regular k. So we're going to actually erase this and move it down here. I know it looks nice, but we're going to move it so that way I have the room to write it here. So we're going to move this to our left, I suppose. 0 to 1 of x squared dx is equivalent to the limit as delta x approaches 0 of the summation k equals 1 to n of, and remember, we're plugging all of this into the function x squared. Remember, in our notation, it was f of x dx. Our function is x squared, so we need to plug in these numbers into the function x squared. In this case, that just means everything will get squared whenever we plug it into here. So this is equal to 0 plus k minus 1. Remember, we're starting our integral at 0, not 1, so that's why we have to put this minus 1 here, times 1 over n squared times 1 over n. So now we just need to solve this, and we can find the area underneath this curve from 0 to 1 of x squared. First, we're going to do some simplification. Instead of it being delta x approaches 0, we want to change this to being n approaching something else. Well, we know what delta x equals. We know that delta x equals 1 over n. Now, in order for delta x to approach 0, what does n have to approach? Well, in order to make this number be 0 with division, n has to be infinity. So, in order for delta x to approach 0, n has to approach infinity. So we're going to change this limit to be n approaching infinity instead of delta x approaching 0. It's equivalent, but it makes it easier on us later. So then this is all equal to the limit as n approaches infinity of the summation of k equals 1 to n of, and we're not going to include this 0 because there's not really any reason to, and I forgot a parenthesis here. Okay. Now we should be correct. We obviously don't need this plus 0 because it's 0. So then simplifying this down, we get k minus 1 all divided by n. 1 over n times k minus 1 just puts the k minus 1 on top divided by n squared times 1 over n. And simplifying this even further, we get the limit as n approaches infinity of, whenever you square a fraction, you just square the top and bottom, and that's the same thing. So we're going to put the summation as k equals 1 to n of k minus 1 squared all divided by n squared times 1 over n. Now k minus 1 squared times 1 is just k minus 1 squared. N squared times n is n cubed. So simplifying this one last time, we get the limit as n approaches infinity of the summation k equals 1 to n of k minus 1 squared all divided by n cubed. Now we're getting somewhere. We simplified this down, and we also changed what our limit is approaching, which will make it easier on us later. Let's now pull a constant out of this fraction. It may not look like a constant, but this n cubed is the same thing as 1 divided by n cubed, because if we were to multiply 1 over n cubed by k minus 1 squared, then we would get k minus 1 squared over n cubed. And remember, this top number in the summation is just a constant, so this n cubed is also just a constant. So we're going to pull that out of the fraction to make this a little easier. The limit as n approaches infinity, or sorry, we're going to pull it out of the summation, which I suppose will also make it not a fraction, but point is, of 1 divided by n cubed times the summation as of k equals 1 to n of k minus 1 squared. Now we're going to have to simplify this down. K minus 1 squared is equal to k minus 1 times k minus 1. So we're going to turn this all into the limit as n approaches infinity of 1 over n cubed times the summation of k equals 1 to n of k minus 1 times k minus 1, which is equal to k squared minus 2k plus 1. There's a lot of steps to this, man. It takes a second. Now what we're going to do is we're going to separate this summation into 3 pieces. Since we have 3 pieces that are divided by addition and subtraction, we can separate them. So now we're going to change this into the limit as n approaches infinity of 1 over n cubed times a lot of things. First of all, the summation as k equals 1 to n of k squared plus, or actually no, minus, since this is a negative over here, minus the summation as k equals 1 to n of 2k plus the summation of k equals 1 to n of the number 1. So we've been able to break this down into a bunch of smaller equations, which will be easier for us to solve. Now you may not recognize it right away, but we have algebraic expressions for these summation series, which will make it a lot easier for us to solve this. K squared is something different, and k is also something different. So let's write that over here in this blank space. We're going to change this all into the limit as n approaches infinity. And by the way, these algebraic expressions that I'm about to go over, I talked about at the beginning of my last integral lesson where I talked about the definition of the integral and the Riemann sum. So if you're confused where I'm getting this from, it's in my last lesson, don't worry. Of 1 over n cubed, this is just hanging out here. Let's change this part into an algebraic expression first. The summation of k equals 1 to n over k squared is equal to n times n plus 1 times 2n plus 1, all divided by 6. And we're going to pull this 2 out because then this k, which is the same here, also has an algebraic expression. So this is going to be minus 2 times n plus 1, all divided by 2, and then plus 1 times n. This last one isn't very complex, it's just a constant. And then to put it in these square brackets, I just barely have enough room here on the board. And actually, one slight correction, this should not be a plus, this should be a minus. Anyway, okay, so what's going to end up happening is we're going to distribute this 1 over n cubed to all of these, and that's a lot of algebra, and I'm kind of out of room on my board. So I'm going to give you what the simplification equals, and if you'd like to in your free time, feel free to do the simplification yourself. This ends up turning the entire equation into the limit as n approaches infinity of 2n squared plus 9n plus 1 all divided by n squared, or 6n squared. This is what this is going to simplify into. Now, once again, we're going to split this by addition since we have 2 points that we can split it by. So we're going to split this into the limit as n approaches infinity of 2n squared over 6n squared plus 9n over 6n squared plus 1 over 6n squared. And now we just have to plug in infinity for all of these limits. Now, via the tower of power, we know that a constant divided by infinity is going to be 0. We also know that a lower power, such as n over n squared, is also going to divide to basically equal 0. The only one we're going to be concerned about here is 2n squared over 6n squared. Since n squared and n squared are of the same power, we can just take their coefficients, and that's what this fraction will equal. So the area under 0 to 1 of x squared dx is just equal to 1/3. We did all this work to get 1/3. I know that may seem like a lot, but don't worry, you will basically never use this after this lesson. But it's important to understand what's actually happening when you take a definite integral. And I think it's very important to understand what's actually happening when you do calculus. Anyways, let's now go over some properties of definite integrals. Number 1, the limit can be interchanged. So I'll write limit can be interchanged. What this means is if we have a definite integral such as the limit as from a to b of f of x dx, this can be equaled to the negative integral of b to a of f of x dx. You probably won't have to use this very often, but it does come in handy sometimes. Next is the integral at a point. So number 2 here, integral at a point. Essentially, if we have the integral, or a definite integral, from a to a of f of x dx, this will always just equal 0. And it's a lot easier to visualize. Let's say we had a graph that looks something like that. Let's get our blue marker here. If we went from a to a, this is point A, and our line looks something like this, our entire area will be bound under a line. And the issue is that lines don't have widths, so there's no area here. So no matter what, the area under a single point, or the integral under a point, is always 0. Next up is the linearity rule. The linearity rule is very similar to rules we visited in the past. Let's say we have this definite integral of r f of x plus s g of x dx. This integral can be split by addition, and the constants can be taken out. So let's change this into the definite integral from a to b of r times f of x dx plus s times the definite integral of a to b times g of x dx. This is a rule that we can use to simplify it into 2 easier integrals to make our problem a lot easier to do. And just like other rules in calculus, you can split by subtraction as well, but not multiplication and division. Number 4 is the dominance rule. And this is another one of those rules that's very easy to explain visually. Let's draw this graph here, and we're going to take 2 other colors other than this red. Let's take our blue and green. I guess the red wants to be on the floor. We'll mark A, and we'll mark B, and these will go upward like so. And we'll have one line, f of x, up here. And we'll have another line in green, g of x. Something like that. Now the area of g of x is this area down here, below the curve and between our bounded points. So it's right there. But the area of f of x is this area up here, which includes all of g of x in this case. This rule states that if f of x is greater than g of x for all f of x and g of x between a and b, then the definite integral from a to b of g of x is strictly less than the definite integral of a to b of f of x. Visually, you can see that the area of f of x is completely engulfs the area of g of x. That's basically what's going on in the dominance rule. And then our 5th and final rule for definite integrals is the subdivision rule. Say we had an integral from a to b of f of x dx. And say we had a weird split, or this graph looked kind of weird. We can actually split this integral into 2 pieces despite it not being split by addition. It looks like this. We can split this and add a variable c in this case. Go from a to c of f of x dx, and then we can just add the integral from c to b of f of x dx. And these two are equivalent. We can split it by a variable. And this comes in handy most of the time with piecewise functions. We're actually going to do one example of the subdivision rule with a piecewise function. So let's do that now, and we'll finish the lesson with that. Say we had this graph here. It looks something like this. And we have f of x is equal to the following piecewise function. This function is equal to 1 when 0 is less than or equal to x, which is less than or equal to 1, and 2 when 1 is less than x, but less than or equal to 2. So let's now draw out our graph so we kind of know what that looks like. First we have 1 and 2 on the y-axis, and 1 and 2 on the, 1 and 2 on the x-axis. This function is 1 from 0 to 1. So from 0 to 1, this function is at 1, so it's this area here, bounded here at 1 and 0. I should probably mention that this is 0 here. But then the function jumps up to 2, but does not include the endpoint 2. And from 1 to 2, this function's value is 2. So it also includes this area. Using the subdivision rule, we could split this into two pieces to make this much easier to solve. And conveniently, this is rectangle, so it won't be very hard to solve at all. So instead of just having the integral of 0 to 2 of f of x, we can use the subdivision rule to split it up. So let's change this, and we're going to split it at the value 1 since this is where we have the jump. This splits into the function from 0 to 1 of f of x dx. And then we go from 1 to 2 of f of x dx. Now, since these are rectangles, we're just going to do these areas by hand. The length is 1, the width is 1, so this part is equal to 1. And then for our second rectangle, the height is 2 and the width is 1, so that's just going to be 1 times 2, which is 2. So 1 plus 2 equals 3. And that's the area under f of x dx, and the answer to the integral of this piecewise function. So that's all I have for you guys today. If you enjoyed this video or learned something, consider subscribing, and if you want to learn more about Calculus 1 or go to previous lessons I mentioned in this video, check out the Calculus 1 playlist linked here. I'll see you guys in the next video.